Good morning. Welcome to Krishna's classroom. So we set forward to define Lebesgue integral, and it is done in stages as we have said in the previous lecture. We first do it for simple functions over sets of finite measure, and then we go on to consider more general class of measurable functions. It will take 2-3 stages. So before that, we had a discussion on the Lebesgue integration, the Riemann integral, and we also pointed out several shortcomings of this. In fact, there is a very elaborate discussion that we did in the beginning, but just one situation we look at by recalling the famous Dirichlet function. So Dirichlet function is a real valued function defined on by the characteristic function of this. Means we are considering the function on the interval 0, 1, now at all irrational points, the function takes the value 0 on the interval 0, 1, and at all rational points the function takes the value 1. So it takes only two values, namely 0 and this is expressed by the very handy characteristic functions. So it's essentially the characteristic function of the interval 0, 1 intersection Q. Now, you know that this is not, phi is not Riemann integral. Why? Because you see that if you go back to the definition of the Riemann integration, you see that it involves taking both supremum and infimum on intervals, and you know that on every interval on 0, 1, you see that there exists rational points as well as irrational points. So at rational points, the function attains its supremum, namely 1, supremum value 1, and at irrational points it attains the infimum value 0. In fact, it takes only values, namely 0 and 1. Okay, so that's fine. Therefore, you see that the lower sum or the lower integral and the upper integral can never be equal. That's what we want in the definition of the Riemann. Therefore, this is not Riemann. Okay. Now we look at another aspect of it, namely, we can approximate phi by a sequence of Riemann integrable functions. So define the characteristic function of where Q1, the countable collection, is an enumeration of all rational points on 0, 1. You know that this is a countable collection. So this is an enumeration of the set of all rational points on this. And now you define phi k. So since phi 1 will be defined as 1 at Q1, everywhere else 0. Phi 2 will be 1 at Q1 and Q2 and will be 0 elsewhere, etc. Phi k will be 1 at Q1, Q2, Qk, that is at a finite number of points, and elsewhere 0. So the collection phi k infinity is a set of Riemann integrable. And the Riemann integral of this is going to be 0 because it's only on a set of only at a finite set of points where this function has discontinuity. Therefore, all these functions are Riemann integrable, and except at a finite set of points everywhere else the function is 0. Therefore, this Riemann integral is going to be 0. And of course, the pointwise limit of phi k is finite. So you can say limit k tends to infinity this is what it is. Now this function phi is not Riemann integrable. Okay. Therefore, if you look at the limit of this, the integral over the interval 0, the Riemann integral over the interval 0, 1 of phi k does not exist. Or I would say this is not equal to the Riemann integral of because this doesn't exist. Why doesn't this does not exist? And this is essentially the Riemann integral of 0 over 0 1 of limit k tending to infinity of phi k so this does not exist. Okay, this is essentially equal to 0 because each one of these 0, therefore the limit of this as k tends to infinity is 0. Therefore, the limiting function is not Riemann integral. Therefore, the interchange of limiting process and the interchange of the limiting process and the integral is not valid. Okay. So, what he says is that you consider the class of all Riemann integrable functions over the interval 0, 1. There exists sequence of Riemann integrable functions whose limit is not a Riemann integrable function. And consequently, the interchange of the limiting process and the integration process thus is not valid for this particular function. So you cannot have a very general result says that the limiting process and the integration process can be interchanged, which is a desirable property that we need while we do analysis. So our problem now is, can you devise a new integration process which takes care of such inadequacy? And that's what we had been trying to do. That's how we were trying to build the concept of Lebesgue integration, and we hope now we can define, we are on the verge of defining Lebesgue integral, and we hope that the new integral process that we define would take care of such inadequacies. Okay, as we shall revisit this example again. So, as I said in the beginning or in the last lecture, we have charted out our path. That was beginning with defining Lebesgue integral for simple functions, and then going over to, in stages, going over to defining Lebesgue integral of measurable functions. So let us start with the definition of a simple function. So let us recall. A real valued function phi defined on a measurable set E is said to be is called a simple function simple function if it is measurable and takes only so what you need is a few things, namely that it is to be defined on a measurable set. Secondly, the function itself is a measurable function. And thirdly, the range should consist of only finitely any values. Now, these are the three requirements that you need for a function to be called a simple function. So, we define the Lebesgue integral for simple functions defined on measurable sets of finite measure to begin with. Later we will go on to generalized. Okay. So let A1, A2, AN n real numbers. Distinct real. That means AI, AJ, whenever I is different from this condition is satisfied. Now let psi defined from a measurable set E to R such that the range of is that is the distinct real numbers and because we take E to be a measurable set and psi inverse of this say is measurable. Then we have psi defined as sigma chi, and we also have ei intersection j is mt, I different from j, since so psi is essentially a linear combination of characteristic functions of measurable sets. Therefore, psi is measurable. A linear combination of characteristic functions of okay, so psi is a measurable. Now we have ei. Ei can be written as ei's are essentially a set of all x belonging to E for which now these ei's are distinct. Okay, clearly that we have said they are the intersection of ei with j is empty for I not equal to j. Now psi, so this one is called the now you see there are other representations possible as we shall see. Okay, but this is what you call the canonical representation, and this is final because sometimes you may be given a simple function because all that it insists on is that the function should take only finitely any value. Suppose you have got a1, a2, etc. an, where ai is equal to aj for some I and j, it is still a simple function. Okay, but suppose the representation is given by this, where ai is different from aj whenever I is different from j, then you see that this property is satisfied, and therefore this representation is what you call the canonical representation. Now what one does is first define Lebesgue integral for psi, a simple function given in the canonical. Now that is quite simple. Okay, suppose you are given a simple function, takes only finitely many values. Some of them may be repeated. Now what you do is, you can reduce that range the functions into finitely many distinct real values. And then you can go about representing this in this particular form. EIs are defined by this, and EIs are assumed to be the measurable. So we are talking about psi measurable. And this is a canonical form that we have. Now we are in a position to define Lebesgue. Okay, let E be a measurable set of finite measure. And let psi a simple function defined on E is given in the canonical form characteristic function of EI, where EI is as given by 2. Now we can define for this function. Now define the Lebesgue integral of psi sigma AI measure of EI. Now you see that everything is fine here, because by our assumption EIs are measurable. E is finite, of finite measure, by monotonicity, since EI is contained in P, we see that the measure of variable I they are measurable. These are measurable sets. These are subsets of E. Therefore, this inequality is satisfied. So they are finite. So in short, what you have is that measure of E for I therefore integral psi over E is well defined. And henceforth, our remark and Riemann integral. This is the symbol that we use for Riemann integral, and this is the symbol that we use for integral. Okay, so that there is no confusion what type of integral we are talking, because we will have to simultaneously look at both together, and then it is better to have clarity about it. Okay. Now the first theorem that we prove is this. Now we ask the following question. Suppose AIs are not distinct. It's still a simple function. Okay. So for a more general class of simple functions, how do you find this? This is the question. So let the collection EI be disjoint now we use this condition for the time being, but later you can see that this also could removed in the statement. Disjoint if disjoint collection of finitely many measurable subsets of a measurable set of a measurable set of I'll put it this way, E of finite. So we are taking E to be a measurable set of finite measure on the real line. Secondly, we take n measurable subsets E1, E2, etc. En as a disjoint collection of finitely many measurable subsets of. Okay, so EI intersection J is empty. For P a real number and phi b defined as AI prime. That means taking the characteristic functions of each of these EIs and taking a linear combination of them with AIs as the coefficients is what you define as phi. Therefore, phi is a simple function, simple measurable function. The Lebesgue integral of phi over E is equal to now the important point here, see, we have defined it in the situation where AIs are all different or distinct, but now we are not making an assuming that. So just remark assume that AIs are distinct. Now you see, this is one step forward from our definition, because in our definition of Lebesgue integral, we have assumed that AIs are distinct. Now we are going to drop that restriction, but retain a condition that EIs are you know EIs form a what is called a disjoint collection of measurable subsets. Okay. Collection EI form a disjoint collection. You remember, while we defined the Lebesgue integration, EIs were defined as phi inverse of AI, that is the singleton AI. Then we found that since AIs are all distinct, EIs satisfy the condition that they form a disjoint collection. Okay. Therefore, you cannot directly apply the formula or the definition to this function phi, because we have not defined. In that case, we had AIs all distinct. Okay. Now we don't anymore have that assumption. This is the major step forward at this stage. Okay. Now let us use that. But then when we define integral, you will have to go through your usual definition, where you have, how you have defined it. Therefore, we will have to list out the distinct numbers from among these AIs. The distinct values. So we will. So you see that lambda 1, lambda 2, etc., lambda k are distinct. That is, lambda I is not equal to lambda j whenever I not equal to j. So hence phi has the canonical form one to k lambda I. What is that? Measure of AI, where AI is defined as the collection of all x belonging to E, for which therefore this is the canonical representation. And once you get the canonical representation, you can write down what is integral. So let us also let for 1 less than or equal to j less than or equal to k, ij be the set of n such that AI is equal So you know that these lambda j's, lambda i's are distinct, but ai's are not. That means that there is a possibility that some of the ai's may be repeating, and then your lambda j has to be equal to at least one of the ai's, and maybe for more than one ai. So let's collect all those things, the indices, in the form of ij. Okay. Then what you have is this. Is essentially the union 1 to k ij's, and this is whenever j is different from r. Okay, now we can write down the integral. Use the definition. So see the path we carefully tread forward, because our definition was original for with the assumption that ai's are all distinct. But in this theorem, we are going to relax that. In that case, we have to reduce the whole thing into the language of the definition. Then only you can apply it. Okay, so we have got the canonical form now. And you know that measure of ai equal to no, because we have assumed that ei intersection ej is empty. That's why this condition is therefore this is what finite entity, and this is true for therefore we have see integral phi over e equal to sigma or let me put it this way. Write down this. This is what we want. Therefore, we have sigma I equal to 1 to n k. For each j you have sigma I belonging to ij yeah, and that you can write as, see, on this collection ai's are all lambda j. So this is equal to sigma j equal to 1 to m lambda j right, and this is nothing but by our definition of AIs. This is what you have. Measure of AI is going to be the sum of the measures of EI. Okay, so let us write. So lambda I, so it is lambda j and that by our definition, this is so that completes the proof. Therefore, we have successfully got rid of the requirement that all the AIs are distinct. So that's what we have achieved in this theorem. Okay. Now we want to go beyond that. However, we have assumed that EIs are all what you call disjoint collection of measurable subsets. Now we want to go beyond this and then drop even that condition, namely that EIs are disjoint collection of measurable subsets. But that needs a small exercise. So what we do is the following. Look at the structure of the class of Riemann integrable simple function, Lebesgue integrable simple functions on the interval, on the subset, on the measurable set E of finite measure. So we do the following thing. And monotonicity. Let simple functions defined on a set of then any real numbers alpha and beta integral over E alpha phi plus psi. This is the Riemann Lebesgue integral. This is equal to alpha times integral of phi plus beta times integral of psi. There's a linear. This is linear. in this context. I mean, in this limited context. Now, moreover, y is less than psi 1. Then integral over y. This is what you call model constant. This is the model constant. Okay, so let us prove this. Since both phi take only a finite number of values on E, we may choose finite disjoint collection EI of measurable sets such that both phi and psi EI. So you see that the two functions are phi and psi are different. Therefore, the sets on which they take constant values are also likely to be different. Therefore, what do? We now define EI as a set on which both phi and psi take constant values. So, phi takes a certain constant value, psi takes a certain constant value. Okay? And split the whole thing into such sets. Now, what do we have? Then we have by this is equal to and that means on EI both phi and psi, phi takes the value AI and psi takes the value BI. Okay, so this is what you have. Phi is equal to sigma AI BI. Psi is equal to sigma BI. Now you see you have reduced this to the case of theorem 1, and we can immediately write down the integral that we have already seen. Here we are not assuming that all the AIs are not distinct, not necessarily distinct. BIs are not necessarily distinct. So and BIs. AIs and BIs are not distinct. So we can use the integral. That's what we have done. Okay. Now for alpha, beta, alpha f, alpha phi plus beta psi takes the value alpha AI plus beta BI on PI. Therefore, hence integral over E is equal to sigma alpha AI plus beta BI to measure of E. So what next? and this can be rewritten as these are all finite sums. So this is equal to which is equal to integral okay. So that proves the linear. Now we work on monotones. Monotones. Assume we find eta to be equal to 5 bilinear. Here we use linearity. Yeah, which is the integrand is positive, so, which implies that proves the monotonicity. Okay. I want to make a few remarks and then close our discussion for the day. So we make something. The first remark is that the assumption we have that, okay, or I will put it this way, because we have assumed that in theorem 1, EIs are disjoint. This assumption means this condition in the light of the linearity of Lebesgue integral. For instance, what happens is, suppose you have phi is equal to sigma ai characteristics ei. EIs are not necessarily disjoint measurable sets. EIs measurable. EIs are not necessarily disjoint. Okay. Then what you can do is, you shall write phi as sigma phi. It's a finite sum where each phi k satisfies theorem 1. Okay. For example, I'll just give an example. Hence, by linearity, which is equal to and that needs little bit of work. Okay. You can try to work it out. So what you have done is, we started with the basic assumption assuming that all the AIs are distinct. The first stage, we dropped that assumption, still retaining the fact that EIs are distinct. And at this stage, we are dropping even that assumption that EIs are not necessarily distinct. I'll just give an example. a simple example. Okay? So let E be the interval 0. Now let me take E1 to be equal to half E2 to be equal to and E3 so let us take some function. So let phi be equal to A1 then integral phi here you see that EI intersection EJ is not assumed. We are also not assuming AIs are distinct. Okay, but let us now work on this. So how do we get this? See, you verify this one. Yeah. So you write phi as phi 1 plus phi 2, where phi 1 is equal to A1 chi E1 plus A3 chi. Now phi 2 you take as, what is it? Going to be A2. Now you see that E1, E2, E3 are all all measurable sets. They are intervals. No problem. And you can verify in this case that integral phi is equal to this one. So what is this? So integral phi this part integral phi 1 plus integral phi 2. And this you can apply the previous theorem. So because they are distinct. Okay. So E1 and E2 are, so if you look at these are representations. So this is A1 measure of E1 plus A3 measure of A3 plus A2 measure of E2. Because here we are using linearity. Okay, because this is equal to A1 measure of E1 this part is equal to That's what I have. Therefore, what is this? So this is equal to the sum that we have defined. Okay. Okay. So that explains it, or you can possibly try to format. So we have got rid of all the assumptions that we have made. In the definition, we assumed that AIs are all distinct. That has been removed by retaining EIs are distinct. Sorry, EIs are disjoint. That also can be taxed and using the linearity of Lebesgue integral. Now we take the remark 2. Now look at the step function. A step function takes but now on intervals. That's a distinction. There you are talking about measurable sets. Okay? Here you are taking intervals. Now intervals are measurable with Lebesgue measure. With the Lebesgue measure, given by its length. Therefore, what do we have? See, the step functions defined on intervals are simple features. Now the measure of singleton is zero. Therefore, what do you have? See, something like, so you can write this in this particular form, that so a step function takes the form that, so if phi is step function, on an interval AB, then AI then Lebesgue integral of phi, this is equal to length of ij, measure of ij, which is equal to Riemann integral of therefore on step functions, the Riemann integral and the Lebesgue integral. A step function is a simple function and the Riemann integral and Lebesgue integral are the same. Now that shows we are on the right track. Okay, we are on the right track to generalizing Riemann integral to Lebesgue. So this is the one. Take comfort in the fact that possibly going forward along the right track. Generalizing Riemann integral. So this is our objective. Okay. So we are along the right track for at least for step functions. We see that both the integrals coincide. Therefore, eventually what we expect is that all Riemann integrable functions are Lebesgue integrable and the Riemann integral coincides with the Lebesgue. So there is some time in between before we reach that. Okay. Thank you very much.